are you all friends now? Now that the assignment's over? All good? Yeah.
Where will grades for the midterm be posted?
They'll be, what?
Where will they be posted?
In your email boxes.
Okay.
We'll email you when those are done. We'll grade assignment 3, so you'll know exactly where you are up until that point. Any other questions?
I saw there's a microphone right there.
Yeah, it's out of battery.
No, the microphone at the desk. Right.
I don't want to use that one, so it's good. It's a handheld mic. I'm not a stand-up comedian, so. I think can you hear me in the back? Let me know if there's any problems. I will yell louder. Any other questions, comments, midterm? Yeah.
Yeah, will the test be handed back in here, or do we just get our grade?
Unsure yet. I think we definitely won't hand it back here. We may give it to you digitally, so you may be able to figure out exactly what happened that way. Yeah.
Is there any way you can kill the static?
Yes. Probably. Like that?
Thank you.
I didn't know that was an experiment that we were doing. Subliminal messaging through static. It was not. Against IRB rules. All right. Well, let's jump right in. Right in. Cool. Okay. So, it's been a long time. Somebody remind us of what the heck we were talking about before we went on this midterm break. Yes?
We were talking about authentication systems.
Authentication systems. What's an authentication system for?
Are you who you say you are?
Are you who you say you are? Or who are you, right? Exactly. Both of those, right? So who are you in accordance to the system? What kind of things make up an authentication system? Yeah.
What you know? What password?
Something that you know. What else? What other types of authentication systems? Yeah.
What you are?
What you are.
Location.
Maybe location. What you have. Anything else that we talked about? Cool. All right, that's good. And so we talked about abstractly. We can define an authentication system as something that tries to prove the identity, our identity, against the system. So we have some complementary information that's stored. We have a function to map the user identity to the complement to that information, and a function that verifies identities. So okay, so we looked at initially just a password-based system, and this was passwords stored in plain text. So what were some of the problems that we discussed when we talked about storing passwords in plain text? Yeah.
If you found the plain text, you've broken the system.
If you find the plain text, you've broken the authentication system because now you know that password, and so you can authenticate as that user. What else? Yeah.
Timing attack?
Timing attack, yeah. So if you don't do this correctly, there could be a timing attack in detecting the password itself. Yeah.
Anyone that has access to the plain text that like work on the website have access to the passwords.
Right, so anybody with access to the website or the database has access to all of these passwords, which they can then use to impersonate other users. Anything else? Yeah.
If they know that password, chances are they use that same password for other accounts.
Yeah, so if this database is ever leaked by either an employee or a vulnerability in the website that allows somebody to leak the password, it's highly likely that that username and password is used on other websites on the internet and the web. So you've basically broken the authentication system there. So then we moved to we initially started very briefly talking about the UNIX standard way of doing password hashes. And so where were traditionally passwords stored in a UNIX system? EDZ password, yeah, PASSWD, right? And that file, as we saw a couple months ago, but we saw is world readable. So clearly putting the plain text passwords of every single user in in the EDC password file that's readable by everyone is clearly a terrible idea, because then you can see everyone's passwords on the system. Actually, a funny side note, did anybody go to our cybersecurity symposium on Friday? Did you listen to the talk by Mike, who was the keynote speaker? He had so he's a pen tester at Bishop Fox here. He's actually a manager, but he started as a pen tester at Bishop Fox, a local company in Phoenix, and he specifically talked about pen testing a website where they had a blind SQL injection, which means they could leak one bit of information from the database. And so doing this, you can eventually get all the information, but they're on a limited time pen test. They couldn't get all the information. So they started leaking the password field, but they saw that it was a crazy like the passwords were being hashed or something. They looked into it more, they figured out what stored procedures there were in the database, and they figured out it wasn't actually a hash-based algorithm, it was using an encryption key to encrypt the passwords. And of course that key was stored in the database itself, so there was a stored procedure called decrypt password and encrypt password that would use the key. So by using that function, they were able to extract admin credentials from this database. So I thought that was, as I was sitting there, I was like, oh my gosh, we just talked about that in my class about why that's a bad idea to use an encryption function as your hashing function. Okay, so we would think that so we just said we don't want to store the passwords in plain text in a shared readable file because everyone can read it. So why don't we just hash them? Hash the passwords. Use SHA-256 and call it a day. Yeah?
Rainbow tables. People can pre-hash a bunch of really common passwords and then just compare them.
Right, so yeah, we looked at, okay, well how would you break this? Well, you can see on the passwords, you know that the string password will hash to a certain value. And so you can actually pre-compute this list of possible passwords. And with rainbow tables, which we may get into a little bit, but the cool thing is that you don't need to store all the data, but basically you can store all these hashes, pre-compute them, and check them against every single user in the database. So we said, well, maybe a better way would be to kind of customize, in some sense, each user's either hash function in some way. And so this is actually the UNIX style of password hashes, or the initial style. So first interesting thing is your password is a string of 8 characters or less. Is that a good or a bad thing? Yeah. Good for hackers? Okay, we'll talk about it from a security, a defensive perspective. Yeah.
I mean, that length of password is going to be relatively easy to remember compared to if you had a really long, complicated password.
Yeah. So you have a trade-off here, right? So the interesting thing is that it limits you to 8 characters. Why wouldn't it let you have a password of 20 characters or 25 characters? Yeah.
Maybe you can take really long to hash.
Possibly, especially maybe back when they were defining the standard in the 80s, 70s. Maybe it took a while.
Maybe they want to minimize hash collisions.
They want to minimize hash collisions. Yeah, that could be, but assuming you have a good hash function with 256 bits of output, if that's what you're using. Yeah, I mean, it's honestly looking at it, it's a clear design flaw, because why would you limit the size of passwords? Like, you should, if somebody wants to create a password with the size of 20 or whatever, just let them do it. It's not a big deal. And so the complementary information, so the basic idea is you'd have 2 characters that would specify what's the hash ID, and you'd have then an 11-character hash of that password. And the idea is these 2 characters, so how many, so you have then those 2 characters map to essentially so this is what we talked about a little bit before, we'll get back into it. Rather than just using a salt that they add to the password, they actually change DES depending on which version of this hash function is used. So they have 4096 versions of DES, and then you have the set of all possible, the set of the login functions as well as the programs that change passwords and do all that fun stuff. So now if you have so now you're looking at this database, how do you break passwords? Or how do you guess people's passwords? So let's draw a little nice, lovely picture. So you now have, so for every user's password, you had some, we'll call it a hash ID, and the actual hash. So for every user on your system, you have this, well, I guess this would be C, the complementary information. So you have a bunch of users on the system. How do you break passwords? Yeah.
Clarify the process again. Like how does this get out there? If you
Cool.
so you have a password and then
Yes, you have a password. Let's call it password. Right? So what that does is you then look up what's this hash ID, because that's going to tell you, essentially you can think of it as this gets passed to some different combination of DES. There is no key involved here, it's just running DES to do that, and then out comes this hash. So the way that they think about it is this hash ID, basically you can think of, you have DES0, DES1, DES2, DES3, all the way up to every different, so this hash ID tells you which version of DES that you use for this. This is before they had really good hash functions that they knew how to use, yeah.
How's the hash ID generated?
Randomly. So when you create a user, you randomly generate a hash ID. So you take their password, you randomly generate a hash ID, you run it through here, and then you save it in terms of the complementary information. Yeah.
What's the length of our alphabet on a hash ID?
Two character hash ID, 11 character hash.
Yeah, but what's the range of characters, I guess, for the hash ID?
That is a good question. I don't know it off the top of my head.
Okay.
I think it's hexadecimal or something approximating that, but I don't know. Yeah.
so the hash ID just comes before the hash?
Yes.
And
Well, I think if you look at it, there'll be a colon in between them to separate them, but yeah.
can't you just use that hash ID and subtract passwords and all of it and then see what matches?
Right, okay, so one way to do it, so to break an individual user's password, right, what would you have to do?
Use their hash ID to
Yeah.
get the DES.
Take the hash ID, figure out which version of DES, and then keep guessing random passwords. Will that information of what you're trying to guess of the random passwords help you break other users' passwords?
Yes.
Only if they have the same hash ID.
Only if they have the same hash ID. Why?
Because if they have a different hash ID, it's a different function.
Yeah, so let's say I have user 0, and this is hash ID, we'll just call it 0. And then I have user 1 who has hash ID 1 with some other hash. If these both have, let's say their password is both password, will the hashes be the same?
No.
No, they'll be different because this hash ID is different, yeah.
Are the hash IDs public information?
Public information, they're stored, well, public in the sense that they're stored with the complementary information, so if you steal the hash, you know the hash ID. Yeah.
Are these actually hashes? Because DES is an encryption system, so does it you use the hash ID as the key or?
I think, no. Technically, it uses, the way it was, now it uses proper hashing with solvent, but the original way it was done is they tweaked some of the parameters of DES, and I think they use a zeroed out key, and they may do it a couple times. So they may run DES on itself on the same input a few times. I don't, but yes, this was before they had a good hash function that they could trust to use. Yeah.
Was there a predetermined one-to-one relationship between hash IDs and the DES version?
Yes. In the sense that if you know this hash ID maps to this version of DES.
And that would be consistent across systems?
Yes. Yes. So, could you create a pre-computed list of common passwords to hashes?
Yeah.
Yes. How would you have to do that though?
Maybe.
Have several pre-computer lists for each.
Right. You have to have 4096 copies of those for for all the possible different hash IDs. You can still do it, right? But that's so the idea is you're making the problem more difficult for an attacker rather than just completely pre-computing this list. And you know, in a given hash function, password always hashes the password. Now with the hash ID, and then the better way to do this is to think of this in terms of salts. So you have the salt and the hash, C0. You use a good hash function like SHA-256. And then, so actually Unix is slightly more complicated. If you actually look at a etc password file or now the etc shadow, it's basically something like the hash algorithm to use, and then the salt, and then the hash. So this hash algorithm would say this password is saved with SHA-256 hashing. The salt can then be, so now when you have the password in, so when you say password, now this goes into SHA-256, and usually you concatenate the salt with the password, and then out comes hash prime, which you then compare with hash. So now by making salt significantly large, now you can make essentially, to break passwords in this, the attacker needs to guess for every single user because they have a relatively unique salt. So it would be difficult for them to pre-compute this. Cool. Questions? Yeah.
Yeah, you said that they moved passwords to the shadow file.
Yes.
Was it just because the other one was more readable?
Let's see. Yes. So they realized, man, even if you're doing this, you could still download the etc password file and do brute force cracking of passwords. And because people usually choose very terrible non-random passwords, right? There's a tension between users of a password that's easy to remember for them and a password that is difficult for an adversary to guess, right? If I just used my first name as my password, Adam, that would probably be something that you would guess or try to guess to break my passwords. Plus, you can do an automated system to do this to break passwords very, very quickly. So they realized, okay, it's not a good idea for everybody to read that file, but that file contains important information. It maps user IDs to usernames. It says what groups those are in. So that needs to be accessible. So now if you see in the etc password file, there'll be a star where the password field is, and that means look in etc shadow, which is owned only by root. So something like login, when you're logging in, that process acts as root to check your password with the etc shadow file. So it uses the setUID functionality to do that. Yeah. Is there any reason? No, I think now I do not believe it is, but that would be interesting to find out. So no, I'd say now the general advice is you should be able to accept passwords that are as long as the user wants them to be, up to a reasonable size. Nobody's going to remember a megabyte long password. Yeah.
What does the salt contain? Is it random or?
Yeah, so the salt would be some kind of random depending on how much. I mean, it would depend on the hash algorithm usually, but it'd be some randomly generated bits of entropy that makes it so that every user should have a different, that you can't pre-compute a rainbow table against any of these given entries. So you want it enough bits such that it's highly unlikely for multiple users to have the same salt ID. Like I think 496 is not big enough. I would probably just do a 32-bit salt or whatever. I mean, something. So actually, the better thing to do is to never write your own one of these and use a library that does it for you. That way you don't have to think about it. Yeah.
So the salt is the hash ID.
here, so the way, I mean, you can think of it like that, but really what it does, the way you do this is that you just, before you, so I'll make the diagram a little bit more correct. So you have SHA-256, you take the salt, and you can either prepend it or postpend it to the password. So this would be concatenation, so you just concatenate those together. You now have a unique string. That way, as long as the salt's different, your password is password or your password is foo. I mean, the password is the same, it will still get mapped to different things. And because this is a cryptographically secure hash function, you can't go backwards. Even if you already knew that salt, you still can't go backwards. Cool. Any other questions?
What's the salt name again?
The salt is just like in before where we had a hash ID,
Yeah.
it's essentially randomly generated, I don't want to say entropy, but randomly generated value that you add to the password before you hash it, such that different passwords hash to different values.
You mean same passwords?
Same passwords hash to different values. Yes, different passwords should always hash to different values. So this way, the same passwords with different salts hash to different values. Yeah.
He was.
Oh, sure.
Okay. If you
We
know,
have enough time. We'll get
if
to
you
all
have
that.
if you find out the salt, would it be still a vulnerable to dictionary attacks?
I don't know. You answer that. Tell me.
Probably yes.
So if you know the hash, or if you know the salt, then what do you also know?
Well, how to like common passwords to this.
So assuming you can get this salt information, what else can you get from this diagram?
The output hash.
Yeah, the hash. So you have the salt, the hash, and the hash algorithm, right? So you have all knowledge of that. So then how do you break the password? Just like before, randomly guessing. The difference is now you have to do that on a per user basis. If you have 1 million users, you have to try to break each user's password individually, and you essentially can't reuse your computation to say, oh, what's password out of all of these millions of users? Or who uses the password QWERTY out of all of these millions of users? You have to test every single person and redo this hash computation. So, but it's still vulnerable to this by, if I said, if this user is user admin, then maybe that's the user I want to break. I actually don't care about breaking any other users. So why can we use a brute force dictionary attack here?
Can or can't?
Why can we? You just said we can.
Oh.
I agree with you.
I said we can if we know the salt.
Yeah, so you know the salt and the hash, you always have to assume they're stored together, right? Fundamentally they have to be. If it's a secret information, then you basically are into the realm of encryption and you have the problem of how do you actually keep that information secret. So you have to assume if the hash is public, the salt's going to be public too. So why is this vulnerable to a dictionary attack?
You can do what we did before. Attach the salt to, append the salt to common passwords. Get the hash compared and then keep going.
Yeah, so you know the salt, you can just keep guessing passwords, append the salt, and check the hash, and find it when you break it. How long does SHA-256 take?
Not so.
256 seconds.
It does not take, that's the number of bits in the output, but good try.
Isn't it used to encrypt connections?
Yeah, it's really fast, right? It's used to, not, I wouldn't say encrypt, but
Oh,
hash.
yeah, hash.
In a lot of areas. I think there may even be an Intel, there definitely is an Intel AES instruction, so they do AES, they can do AES on the chip. There may also be hashing functions like SHA-256 on the chip. Why do you want it to be super fast? What was the point of a hash function?
Time attacks.
Maybe timing attacks, so you want to reduce the time it takes to, there's other stuff involved there, but yeah, part of it. What else?
Utility.
If it's slow, nobody uses it, right? And what are hash functions used for, not in this context? integrity, right? The integrity of a message. I can send you the message and I can send you the hash, and you can compute the hash across that message to verify that it's actually what I sent. And if that hash is slow, if you're trying to run a hash on gigabytes of data, you'll never do it and nobody will ever use it. So you have this really interesting property. A hash function needs to be as fast as possible. In this case, is a fast hash function good?
No.
Why not?
Because it makes, if you're being attacked, then it's easier for them to brute force because it takes less time.
Right, because once an adversary gets the salt and the hash, the faster this hash function is, the more passwords they can try in a given amount of computation. Right? And if it's in hardware, they can do it very, 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 very fast. So what do we do? Yeah.
Oh, I had a different question.
Sure.
When we were talking earlier about like pre-computed tables,
Yes.
how does that work if the salt is randomly generated?
You fundamentally cannot have a pre-computed table. You need to compute. You can't pre-compute it. You need to compute it here when you have this specific user that you're trying to break. There are more hands here. I'll go back to what I was talking about. But question?
You answered it.
Okay. Wait. We're gonna go back. So the problem is that it's fast. But what other properties do we want about the hash function? Should we just use something like CRC32 or? Yeah, we want to make sure that passwords that are similar to each other, QWERTY versus QWERTY1, should hash to completely different things. What else? Yeah.
They should have pre-image resistances.
Pre-image resistance, meaning?
So you can't find two messages that hash to the same value, and then you also can't take a hash and go back to find the message.
Yeah, and specifically, I mean, here we really care about that part, right? We don't want to be able to take the hash and just go back to the password, right? Without guessing all possible passwords. So should we just get rid of the hash functions in general?
Yeah.
What are you going to replace it with?
Blind trust.
Better passwords.
Better passwords. Yeah, good luck with that. I will just say that's impossible and we'll continue on. So it's a tricky problem, right? You have these properties, cryptographic properties that you can look for, and they're proofs, things that, theorems that will try to prove these things, these properties of these hash functions, which you desperately want, but they're very fast, and you don't want that part. So what do you do? Yeah. How do you make it slow? Come up with a new slow hash. Yeah.
Make the password or salt larger, or I guess not the salt, but just the password.
Maybe make the password. How do you make the password larger?
You can increase the characters that are allowed, or you allow the length to be larger and set like a minimum.
Force people to use like 100 character passwords.
Yeah.
I think the difference between hashing 8 characters versus 100 characters is minimal. I think you need to get to the gigabyte level.
But then when they're doing a brute force attack, it takes much longer.
Because
the password space is larger.
Okay, so if you're requiring them. So basically, okay, so good. So one thing would be, with the passwords, make it so that the search space for passwords is huge. So if you require every user to have an 100 character password, of course, what are they probably going to have as their password?
100 A's.
100 A's? Yeah, that would be my first guess. Or maybe just 100 zeros, or I don't know. Honestly, probably nothing. Like, nobody would use your system because it would be impossible to remember or use an 100 character password.
I mean, if no one uses it, you know it's secure.
It is very secure. Yes, exactly. I'll agree with that. I wish you good luck with your no user service. Okay, so that's one way, but that is fraught with error and peril, because even if we try to help users create difficult to guess passwords, it's hard to make that actually do that well and in such a way that they'll remember it and where they won't just do things that completely undermine your security. Yeah?
Hash it multiple times?
Hash it multiple times. Why would we do that?
So you could make it longer to crack because you have to do that operation multiple times, but also...
So how many times? Twice?
Probably more than that.
Probably more than that? Yeah, maybe 5, 10, well, that's maybe still not going to do it. 1,000, 100,000, 1,000,000, maybe? So, okay, so then let's think about that. So, what would be, let's say a good, I don't know, what are you gonna target for? What's the time you want it to take roughly?
A year.
A year? Okay, let's go with that. So 1 year. Okay, cool. So this process takes a year. So now how long does it take to create a user?
1 year.
How long does it take to log in?
1 year.
Is this a usable system?
Yes.
No. Okay.
Maybe like 5 seconds.
So you want like 5 seconds? Okay, so then let's think. So signing in,
5 seconds.
can it take less than, or let's say creating a user.
5 seconds.
Can it take less than 5 seconds?
Maybe.
How?
So, if it's like a multiple like page user registration, when they enter their password, you can do the hash like then, and then.
Okay, you could technically create the hash in parallel. Okay, so what about logging in?
5 seconds.
Can it take less than 5 seconds?
Probably not.
Why? Right, you have to perform the exact same operation. You have to hash for however many millions of times it takes for it to be within to be done in 5 seconds. And then once you do that, you compare the hash with what you've got stored, and then you let the users into your website. Now, if we flip that around and say we're an adversary who has broken into this website, how many passwords can I guess per second?
0.
Password.
Like a fifth.
A fifth of a password, right? Yeah, so 0.2 passwords per second. So it's going to take me a long time. How long is it going to take me to try like the top 10 or 100 most common passwords?
500 seconds.
Yeah, like 500 seconds, right? That's pretty slow. Like, I mean, I guess it depends on the value of these passwords, and maybe they will announce, but this is just for one user. If we think about having 1 million users, we've added some security in here because we're able to do this. So the tricky thing is, so if you set this password to be for 5 seconds, what's it going to take a year from now?
Not 5 seconds.
Maybe not, I don't know, but likely less. It's possible that it takes less and less time as computers get faster and faster. And so, but anyways, this is the basic idea of creating kind of hashing functions that are either slow in this sense. Usually I would not say 5 seconds. I'd say on the order of like 1 second is usually what you want. Yeah.
What about those systems that like lock you out for like 30 seconds after?
Okay, perfect. So, well, we are going to get there, but we could just keep talking because it's much better. So, in this scenario, what do we assume that the adversary has? You tell me. The hash. They have the hash. They've broken into the database somehow. They have the hash and the salt and the hashing algorithm, right? So in this case, so we call this basically an offline attack. In that I don't have to ever ask the system if this password is right or not. I can just look. I have the hashes. I can perform the computations and compare hashes. That's different than, can I still try to guess and break passwords even if I don't have hashes?
Yes.
Yeah, how? Yeah.
Just keep entering passwords. And
Yeah, just go into the thing, figure out either usernames or email addresses, go to the thing, try foobar@gmail.com, password, right? So the difference is that's an online attack because you are interrogating the system itself. And then you can do all these kind of things like exponential backoff and wait. So you can wait for the user and see, okay, you can actually artificially enforce a 1 second delay in here, and then a 2 second, 5 second, 10 second delay in here. But the problem is if that delay is artificial, it means that, so let's say you have a 1 second here artificial delay, and you're doing SHA-256. For offline mode, how long is it going to take them to guess one password? Yeah, SHA-256 time, which is incredibly, like in the milliseconds to nanoseconds time frame, right? So this is a core concept to think about. Like, it's good to put defenses here on online guessing. Anyone ever accidentally wipe a cell phone? No? I have a friend, so Microsoft, a lot of companies, if you join your cell phone to their network, or if it's a work phone, they'll put a policy in place. So have you ever done that where you try to log into somebody else's phone with their passcode? You try once, error. You try a second time, error. You try a third time, it says you're locked out for 30 seconds. Have you ever waited? You try again, you're locked out for like 3 minutes. Do you know what happens after that? Well, depending on your policy, the Microsoft one wipes your phone. So one of my friends was messing with another friend and did that, got to that last part, and then just like wiping phone. And yeah, luckily they had all the data off there, so it wasn't a huge deal, but yeah, you can have pretty crazy mechanisms here. And actually, even on the reverse side, I don't know the state now, but we were looking at like iPhone security and iPhone forensics and trying to break pins. And you used to be able to, I think it was on the iPhone 7, I saw this device in my office. You get this device, you hook it up to a certain part in the phone, and then you hook the other one up to I think it's the lightning cable at that point. It would guess passwords, and when it got to that thing, it would actually just shut off the phone through that other hardware thing, so it wouldn't set that thing that says wait 30 seconds. And so it would restart the phone, and it was able to guess like a 4-digit pin within a day. Even with that stuff, so.
I think that was the iPhone 4, was when it was first vulnerable to the.
Yes, so there were software-based ones that you could tell it to not do that in software. This one required like a hardware device on the phone, so it could kill it before it was able to say that. Yeah.
So the phone was able to turn off and back on in under 30 seconds.
Yes, so it'd be quick enough to keep guessing when you got to that point. And my timings may be off, but it was within the span of a few days you could break into a passcode of a phone, even if it had those features. So yeah, basically turning these offline components, disabling them, so you're essentially trying to do the speed as far as you can get to an offline kind of attack. Yeah.
So then, like, you said it was like iPhone 7, so like what would they update to make that like not be able to?
I believe now, if I remember correctly, so I think they call it the security enclave, which is what they have. So the same place that stores your fingerprint and does fingerprint checking, it's actually not in the kernel. It's in a separate part of the CPU called the secure enclave. I think it's similar to Secure World on an ARM system. I think that's what it's actually using under the hood. And basically, they do. I think they do everything in there. So they probably have ways to like. That's all secure storage. That even if you rooted your phone, you still can't touch and mess with that storage area. So I think that's how they're able to get around it. But I would not be surprised if there's still other hardware-based bypasses for it.
Yeah, as I remember, if you replace your like home button, like
Mhm.
your phone won't work, you have to replace the whole like motherboard or something.
Yes.
That's the thing on it.
Yeah, it's because that's secure enclave stuff. Cool. Yeah.
So when we're talking about making SHA-256 take longer by hashing it multiple times, what would the advantage of, the advantage of that would just be that you can use SHA-256 in multiple applications, because I'm just wondering, like, why don't we just make a hash function that's slow then? Because that seems to be what we're doing anyway.
Exactly. So there's different, and there actually is a need for slow hash functions. The problem is, when you're developing a slow hash function, how do you know your implementation of it isn't slow versus the actual underpinnings of the algorithm are really slow, right? Because if let's say you made a version of SHA-256 that was super slow, that took, whatever, 5 seconds per hash or 1 second per hash. Now, I'm an attacker, I study it, I build a version on an FPGA to do hardware-based hacking of it, and now it takes milliseconds to do that computation. Because when you do this, you basically incentivize people to do that. So yeah, there's a couple different things. So script was one of the first in this area of trying to make a deliberately slow and tunable hash function. And then there's bcrypt. One of the things I think with script, if I remember correctly, script uses basically hashing functions, and it uses a fixed amount of memory. And so it's easy to turn that into create hardware to do that very fast. Bcrypt, I think, deliberately uses a lot of memory when it's doing its hashing, so that way it's hard to do that on an FPGA without it being very expensive. But yeah, there's a whole basically research component to there of developing now these slow hash functions. Cool. Okay. Well, we already kind of went through all of these. Going back here, so this is an example of the etc password file of Alice with her password here. So the first two characters here are the hash ID. The rest is the hash. And excuse me. Cool. Okay. So we actually have already been covering a lot of this, but now we'll kind of mix in our intuition of what we were talking about of attacking these authentication systems with more of that notation that we talked about. So what, okay, let's talk about this. What is the attacker's goal? Yeah, wait, sorry. Yeah.
To get the password?
To get what password?
To an account.
So one goal could be just get a password to an account. Yeah.
To get maybe a specific level password, like root password, for example.
Get a specific user's password. Yeah. To authenticate as the target, does the attacker always need the password to authenticate as the target? Maybe. Maybe there's some bugs in the authentication mechanism which allows them to log in as the user. Did I tell you about the Dropbox bug?
Maybe.
I don't know if I have it in these slides, but I don't think so. There's a bug, I think it was back in, I want to say 2011, it may have been 2009, 2010. You can actually Google this because I have a blog post where Dropbox, somebody realized they logged onto their Dropbox account on the web and they knew they fat-fingered and mistyped their password. They hit login and they still logged in. So they logged out. They tried putting, I think, a friend's email address in there with a random password, hit login, and it logged them in. And so then they emailed Dropbox, and some developer had pushed a fix to some code. I think it may have been like an equals versus double equals kind of a problem, but they'd accidentally pushed some code to production that essentially disabled the authorization check, or the authentication check. So you could log in as any user without a password at all. So these things happen. These could be bugs. They could be, we'll talk about later, some more software-based problems that you can use to bypass authentication. And so, cool. So basically, this is just a more formal description of what we were talking about, right? The attacker wants to find some password to log in, or maybe wants to find a specific user's password. And this was what we talked about. So you have this offline versus offline, online versus offline mode, where online you are querying the service itself, whereas offline you have basically the complementary information and you're trying to figure out the password. Cool. Okay, and this we talked about already. You could try to hide stuff, but you still, like we said, it's hard to hide these. You know, you can't make the assumption that these, if you're storing passwords, that the passwords are going to remain secret forever. The internet is littered with password breaches, so simply relying on that is going to be a terrible idea. Other things, so this actually has to go into kind of a similar topic of what we talked about when we talked about encryption. So can we hide the login mechanism? L?
For certain systems.
For certain systems? Like what?
If you have to go to a specific location to access it, that might be a way.
Okay, maybe if you have to go to a specific physical location to try something. What else? So L would be the login function. So can you actually keep it? So think about it this way. So if you can keep L secret, can anybody break passwords on your system? No, because they have no way of telling if a password is correct or not. But can you actually keep it secret? What was that? Yeah.
Not practically, because then it becomes part of the key essentially, and it has to exist on every server that uses that.
Yeah,
So-
similar to the encryption problem, right? It's like, yes, okay, you could make your own custom encryption algorithm and never tell anyone, essentially, but now the algorithm itself becomes part of the key. And here, now your login function becomes essentially part of something you need to hide. And where are you going to hide it? You're going to hide it in the source code that's running on your servers. I mean, something has to actually do this login function, so it's best not to rely on that. Yeah.
If the authentication mechanism was something like a blood test, what would L be in that case? Would it be like what they're checking in the blood to figure out?
It would be the method of, because you just can't, I mean, you take a blood sample, but you can't just, I don't know, at least I don't think you can just compare blood right away, right? You have to take the blood, take features from the blood. You take probably the blood type, you'd probably take some other features, and then match those against the features that you've stored.
So, in that case, would you consider that to be hidden or not?
I would say no, because your features would need to, I mean, well, you could try to claim that you've hidden L, but fundamentally, I mean, it would not be terribly difficult to figure out what features are you comparing, right? And then figure out a way to break that. Or try to bypass it or brute force it. I get 1,000 people and keep trying blood samples until I match the one that.
But in that case, it feels, I mean, it might not be hidden like the process, but it's not like doable by most. I mean, I'm gonna say like everyone, but like I guess most people, like maybe if you own like a lab or something, you can do it.
I think it depends on your threat model. In this case, so since we're already talking about something that most people don't use, like blood-based authentication, I would say that you'd probably be worried about nation-state level adversaries. And part of what they do is intelligence gathering, so figuring out what features you're matching against would be one of those things I would expect them to be able to figure out. And I would not rely on them not being able to figure that out. That also makes sense. Cool. All right. So, we've been talking about this a bit. So, okay, what was the first computing device where you had to have a username and password? Do you know?
The computer itself?
Maybe the computer itself to log on? But how old were you? This is what I'm trying to get at. Huh? What age did you first use your first password-based authentication system? 7?
Very young.
You what?
My Neopets account.
Neopets? Oh, nice. That's old school. So, long time. So, how do you feel about this? You've been using these systems for a long time.
They're okay.
They have their flaws.
They're okay, they have their flaws. We'll be more specific. Thoughts? And you are the people who use these things, right? It's not just, I mean, literally everybody uses them. Yeah.
They can be hard to remember.
Passwords can be hard to remember. Has anyone ever forgotten a password? Yeah. Sucks. Okay. Can be hard to remember.
Sometimes, like username.
Yeah. Oh, sorry. Let's go over here first.
It's really annoying, like, if you try to be, like, smart and have, like, a long password, then you have to fill in a long password all the time.
Right, so you have that user experience problem where you either intuitively or you've learned that having a long password is better. So you want to have a long password, but actually typing that in every single time correctly is a huge thing. Yeah. Oh, yeah, sorry.
Usernames or like emails can be hard to remember as well.
Yeah, usernames or maybe even usernames. So that actually is a problem sometimes of like what of all these emails or usernames that I use on this site. Yeah.
Policies regarding passwords can make it more difficult.
Say it again?
Policies regarding passwords.
So can you elaborate a little bit?
So some sites have like policies of you can have special characters, but only specific special characters. Then other sites will have, you can have any kind of special characters or, you know, and then there's anything in between.
Yeah, some of like your password can't start with a number.
Yeah. Or your
some ridiculous
password
stuff.
can't have exclamation points or at
Right.
symbols.
Yeah, or spaces. Can't have spaces in a password. Yeah, that's good. Yeah.
Yeah, and as an addendum to that, when you fail to log in on a website like that, it usually doesn't tell you what its requirements were when you make the password.
That's always very annoying. I do hate that as well. Yeah.
Everything uses a password, so you have to remember like a ton of them.
Yeah, not just passwords, but what you have on your credit cards or debit cards. You have PIN numbers. Your phone probably has a PIN number backup. What other non-standard devices use passwords? Those are just two that came to my mind. But
Car doors.
car doors. Oh yeah, I do know some old ones like that. What was that?
Some locks, like, I know I locked my house and it said passwords to it.
The house lock, maybe a combo lock for your bike. Work passcodes. Yeah, we had that at when I worked at AT&T Government Solutions. We had like a passcode for the door to get in. Yeah.
Garage door, still a door, but
Garage doors. Yeah, that's good. A different password for the garage door. So how do you manage all of this complexity? And you've been dealing with this for a long time. How do you actually deal with it? Not how should you? Yeah.
That was my answer.
Actually, really? So you both actually use
Yeah.
password managers?
I don't
So how so? What do you use?
LastPass.
LastPass? And how do you use it?
That was super complicated, really long password that I remember for the master password.
Mhm.
Or like a backup, like a sentence thing that it gives you. Just that, and then like 2-factor, stuff like that, and then just generate new password for you have service every time.
Nice. Anyone else?
Black book.
What was that?
I write down my passwords in a black book that I keep somewhere.
Yeah, so that's not a crazy idea. I would advise not to put it as a post-it on the computer itself, but yeah, having hard copy backups is not crazy. Yeah.
Master password.
Master password?
Yeah.
Can you explain?
Master password is an app you can get on Mac or it's online.
Mhm.
And you have one really long password in combination with, I guess it could be anything, but they tell you to put your name in. And then it automatically generates passwords based on any website that you put in.
Nice. Okay, so kind of algorithmic based in some sense. So it's not just a completely random password that you have to store, but based on, so almost like a hash in some sense. So based on your password and your name, it then will spit out a unique password that you use on that site. That's good. So then you use that app instead of remembering the unique password per site. Yeah, that's good. Yeah.
passwords for sites I don't really care about, I'll typically reuse password, which is bad practice, but I don't really care about what passwords or what systems people do on those sites anyway.
Yeah, I mean, I did that for a long time. Like, I had my basic password that I used on really crap sites, and then a slightly more sophisticated version, and then like my email and banking sites. But now they're all random with password managers. But what else? Any other strategies? Yeah.
After you set up the password, you log out and you log back in, and log out and you log back in, just so you get developing muscle.
Oh, nice. Okay, that's a good. Yeah, I hadn't thought about that. That's good. So actually using the password by logging out, like once you log into a website and create a password with it, log out, log back in, log out, log back in, so that you develop more of a muscle memory for the password. Yeah.
Formal practice, but let Google Chrome remember it for you.
Yeah. So you can let your browser. Yeah, it's very tricky because those are usually not encrypted. So you can, I think, encrypt them, but even then, it's not. Yeah, I think the usability can be an issue there. Of like, then you have the problem of, depending on what the password is, right? Logging in on your laptop versus your tablet or mobile device. I mean, all those things can be tricky, like syncing between devices. Yeah. Cool. So, yeah, please.
I have a base password that I use, and then I change certain things throughout it for different websites.
Cool. So this is kind of like the master password idea, but with your own custom algorithm that you use. Awesome. Anything else? Anybody have anything else crazy? Do you ever find that your algorithm can't get past the requirements of the site, like we talked about?
Sometimes they don't allow certain characters that are in like the base part of it, so I have to change those certain characters, which it's always
bad when you have to take out characters that the website doesn't allow.
Right. Yeah, that's the huge pain with a lot of those things. Cool. So, do you feel that this is a good thing? Like, is this state of authentication to computers, websites, all those things, is it a good thing?
It's okay.
Yeah?
Yes.
Yes? Why?
Because what you know is the most secure.
Ooh, what you know is the most secure. Interesting. Could you know something else that's not a password?
No.
That's the only thing?
I'm gonna say like no, it's not ideal. Cause I don't know, like I think like in like a dream world, right? Like there'd be some system that like right, where like you don't even need to like log in or something. Like you just know, and then you just log in.
Yeah, it knows who you are, right? Your identity.
Theoretical, perfect.
Right, rather than having to continually prove yourself,
Yeah.
it would know who you are. Yeah.
I like things like Face ID or fingerprint authentication more than password, just because easier to use, and obviously, like in a perfect world, it would be more secure.
Right, so yeah, so then you have this problem of, man, like having Face ID or whatever, or a biometric type thing that you actually is very little effort on your part to use, right? That clearly has a lot of the good drawbacks. On the flip side, has anyone ever unlocked somebody's phone by just pointing their phone at their face? I did that last week. It works really well. Or this happened at, I don't think when I was there as a PhD student, but my lab at UC Santa Barbara, somebody unlocked somebody else's phone while they were sleeping. They took their phone and took their thumb and put it on the phone while they were sleeping. So you have problems there, but man, as far as usability, it's pretty usable. So, yeah, I think this quote, I think it's Churchill, I believe, is credited with the quote about democracy, and it applies equally well in passwords, where passwords are, in my opinion, the worst form of authentication, except for all those other forms that have been tried from time to time. So, yeah, like we talked about, it's such a pain, right? And you think about, to use this securely, you should have a unique password that is difficult to guess. For who?
Everyone.
For everyone, not just people, but computers too, right? And they analyze password databases to figure out what are the most common passwords. So you could think that you're being insanely clever because you have this password based on some keyboard combination that looks incredibly random but is trivial for a computer, and a computer will likely guess it, assuming it can guess the passwords fast enough. Yeah, what about, we didn't actually talk about this, but what about snooping? So you can easily watch somebody typing in passwords and guess their passwords. What are other ways that people can snoop on your passwords? Yeah.
I mean, if I know that you mostly base your passwords off of like Winston Churchill quotes, I can go like, all right, I'm just going to get a list of common Winston Churchill quotes and try that.
Shit, I gotta change the passwords now.
Yeah. Keyloggers, right? So what's a keylogger?
Malicious software on your computer that.
Yeah, malware that gets installed on your computer that is listening to all your key presses. So it can see all the key presses you're making to the website, steal your passwords. Yeah.
I heard that there was like a webcam. Like if they hack into your webcam, see the reflection of the screen from your eyes and like the keyboard, and that's how they guess it also the sound analysis.
Yeah, so there's actually been a lot of research papers demonstrating that with your laptop, you can, the acoustic sound of the keys you press, each key is different, so you can build up models and try to guess passwords based on what keys they're pressing. So you can do the easiest one of all, shoulder surfing, where you look over somebody's shoulder and you watch them type their password. Also very easy to do. Extending on that, there have been, all kinds of things where I can film you logging into your laptop, and I can use the reflection of your eye on the screen on your keyboard to figure out what keys you're pressing. It gets even worse. So thinking about your cell phone, so you know that all of these have super awesome like gyroscopes in here that tell you exactly like the location and orientation of the phone. It turns out most apps and now even websites can get access to this gyroscope data. So what happens when you're typing in your password onto your phone like this?
It's like
You're slightly tilting and slightly moving it enough that these gyroscopes can detect. So there's been other work that's been able to determine passcodes based on gyroscope information. Yeah.
I've noticed this for those passwords where you make a pattern or whatever.
Mhm.
You can see where they've slid their finger on the screen.
So that's called a smudge attack, where you look at like the smudges on the screen, and you're able to redo their patterns. Yeah, exactly.
Isn't that the same as like the keypads that wear off?
Yeah. So this was a. This is why if you've been to like a secure facility, rather than having a numerical pad that's 1, 2, 3, 4, 5, 6, 7, 8, 9. Because what will happen is people will put in the passwords in the, everyone will do the same passwords and the keys will not have even wear, so you can figure out the passwords there. So what they do is they have a digital screen that randomizes the numbers every time, so that the exact presses are different every single time. There have even been, going back to the cell phones, they've done research that shows you can actually, if the cell phone is on the desk where your computer is, they can get what keystrokes you're typing into your laptop from your mobile phone. Yeah, crazy. How the emanations that you make when you're typing is enough to perturb the gyroscope, and so you can train and learn on that. And each key press will be kind of different because of the way your finger presses it and where it is, and so it will generate different things. So you can steal keystrokes that way. It's crazy. Yeah. The more we talk about it, the more I think we should just burn everything down. Easy to lose. We talked about this, right? Easy to lose, forget passwords, and then it's gone, right? It's something that you knew, and now it's something that you don't know. But you're still you, even though you've forgotten that piece of information, right? And so there you have that authentication problem. No control on sharing. Does anybody share passwords here? Anyone use a shared password? There we go, that gets one. Yeah, which makes sense, right? There are certain times you want to share access to a resource with other people, and maybe you don't want to reveal that password because you use it on all of your other websites, right? But it's difficult to restrict it, right? I can't say I want to share with you, but you can't share with anyone else. And then all of a sudden, like, you can't watch Netflix because there's 5 devices using it at once, and you've lost control. So, what's social engineering? Yeah, second. Yeah.
The human element behind some of this, so kind of similar to looking over someone's shoulder, or basically getting to know that person and using that information that you find out about them to guess likely passwords that they might have come up with.
Yeah, yeah.
Yeah, I was gonna say like convincing someone to give you information that they shouldn't be giving you.
Right, so that would be like if I'm at my desk in my office and somebody calls me and they say, hey, this is ASU's IT department. We're really worried that there's been a breach of your account. Some user records may have been accessed. To verify that you are actually Professor Adam Dupay and you own this account, could you please recite your ASU password to me so that I can verify who you are before I tell you the extent of these problems, right? It would be very easy for me to give that password over the phone, not realizing that no ASU employee will ever ask for your password as a means of authenticating you. So this happens all the time in a lot of different, and even, so you can even, there's been lots of cases of social engineering to bypass authentication mechanisms. So there's, I feel like we've talked about this, where they've been, if you look for social engineering DEF CON videos, you'll see cases where people will, where a journalist will give them permission to call their phone company and to change the phone address and password over to them. And they pretend to be, super busy, or they give them some sob story and convince the customer support representative to change the password, even though they didn't actually authenticate to the system.
Is that the one with the baby crying?
Yes, that was the one with the baby crying in the background. Yeah, they'll use a recording of babies crying in the background to be like, oh my god, my kid's so sick, and we really need to pay this bill, and it's such a huge problem, and we can't get into the website. Please, let us in. And anyways, it's super. Everyone thinks that they won't fall victim to these type of things, but they are usually wrong. Yeah, so so password reuse, and so many problems, and it really requires each person to be vigilant, right? And we're putting a lot of kind of burden and complexity on individual users to be able to use these systems correctly. So it's kind of a crazy thing that we actually do work. Basically, so this is a recap of what we already talked about. Dictionary attack. So we can just guess from the dictionary or from lists of commonly used passwords what we think the user's password is. So you know the way to think about this is that you don't think about like a dictionary. You don't start with like aardvark and guess that first. Then whatever the next word that, like, you don't start with the A's and just work your way down the dictionary. What do you start with?
Password.
Password? The most commonly used passwords, yeah. So there are studies you can look at. There's all kinds of crazy stuff. So you would guess not by necessarily the dictionary order, but you'd look for words in the dictionary and you'd look in the order of most likely to be a password. Okay, there are offline tools to help do password cracking. There's a program called Crack. There's a program called John the Ripper that you give them hashes and they will try to use all the CPU resources you can give them to crack those passwords. You can even just, if you get sometimes an MD5, you can just Google for that MD5 and you may find the word that corresponds to the hash of that MD5. So when we talked about online attacks where you're trying to log into a website to try to guess a password. So let's say that, oh, well here I guess we're getting here. Okay, cool. So how do we try to defend against password guessing? So we've talked about some of these things, so let's kind of sum up. Yeah?
So if you were like, if you fail 3 times, you get like an email confirmation to reset your password.
Right, so I can add some delay and some pushback in the, let's call it the online method. Yeah.
Offline, we can make the hash function take longer by hashing it multiple times.
Make the hash function slow so that both offline and online are slower. Yeah.
Two-factor authentication.
Two-factor. So force the users to use two-factor authentication. So specifically, don't just rely on the password. Have them give you something else that they know, or something that they have, right? Or maybe a biometric in addition to that. So you could just try to. This is the optimistic way. Is just don't give them access to your database of password hashes, and so force all guesses to be online. But as we talked about, this is very hard to guarantee, right? There are many different ways that your password hashes can leak out. So like we just talked about, add delay to L and increase time to compute. So let's say that a website has done, we have a website. So you say add delay to L when incorrect. So what is that? How do you actually do that? Yeah.
Like offline or online?
Well, let's say online.
In that case, you could, you can keep track of like how many times someone has tried to log into this user account in the past X, like in the most recent minute or something, and if it's like over a certain threshold, then the next time they can log in is pushed back until some future date.
Cool. So now you're an attacker. How are you going to try to break and brute force passwords in that way?
Multiple instances.
You can want to switch accounts.
Switch accounts, right? So
you can also deny access to someone's account that way too.
And then possibly use it as a denial of service attack against them, right? So if we have a thing that says if somebody has incorrectly logged into this account, let's say 5 times in the last 5 seconds, then what we'll do is try 4 times on that account, switch to another account, try 4 times on that account, switch to another account, try 4 times on that account, going basically under the system. Other ways to do it, if you try to use IP address-based blocking, where you can only guess a certain number of times from a certain IP address, I'll rent a botnet, get access to thousands of IP addresses, and have each of them guess one user account every half hour or something. right? Now I'm doing guessing at a very slow level, but across a wide swath of user accounts. Yeah?
I have that stuff for like some websites, even once you log in, like if this is your first time logging in from like a certain location, you can't actually get access unless you verify agreement.
Yes, so that's, and so the other thing to think about, and that's basically all of these things, two-factor authentication, this type of thing, is basically because passwords are so terrible, and because it's easy for websites and, sorry, not websites, but malware to steal your password, they may do other types of defenses where they say, Gmail does this. If you log in from a foreign country, it'll say, hey, this is a little weird, like, verify on your, like, we're going to send you an email about it, and maybe verify on another app that you're actually logging in from this other country and it's not somebody else. Okay, cool. So rainbow tables, as we've talked about already, basically pre-computing some of the hashes, so when you're trying to attack a hash function. Very cool. They trade off. They're super interesting because they trade off time to crack versus space. And the way to think about this is they require a lot of space. So for MD5, all 1 to 8 alphanumeric characters, the table is 127 gigabytes. Going up to just one additional character requires 690 gigabytes of storage to store that rainbow table. But you can easily look up from a hash to see if it's inside that rainbow table. So you can take an MD5 hash, look up basically instantly whether it's a 9-character alphanumeric password. You can actually go and download torrents of rainbow tables for various hashing functions of various sizes. And then you can plug those into tools like John the Ripper to break passwords. Okay, cool. We talked about salts. Wait, we're almost here. We might as well just. We actually talked about all this. We talked about slow hashing, bcrypt, scrypt. I guess I had my roles reversed. Bcrypt was designed to be a slow hash. It's actually used on the submission server, and computing a hash takes 300 milliseconds on the server. So if any of you was able to exploit the submission website to dump the database, it would be very unlikely for you to break people's passwords because it's a pretty slow hashing function that takes 300 milliseconds to compute. And scrypt is the improved version of bcrypt that's designed to take more memory. Cool. Okay. We'll come back and we'll talk about an instance of password reuse.